when molecules or atoms in a given medium are vibrating, this amount of vibration depends on their temperature. In fact, it could rather be said that the average kinetic energy of motion of all of the particles in a medium is proportional to the temperature. So a temperature is a measure of the kinetic energy of particles. Now, when particles vibrate, they emit electromagnetic radiation. And the higher the temperature of a medium, the larger is both the frequency and the amplitude of vibration. So the higher is the kinetic energy of the particles, the bigger is the amount of radiation emitted, and the wavelength of this radiation is also different in a sense that there is a bigger tendency to emit high frequency radiation when there is a high frequency vibration. So there is a direct relationship between the frequency of vibration of a particle and the frequency of the light or the electromagnetic wave that it emits. Since objects vibrate at any temperature unless they have a 0 Kelvin, which is impossible to reach, then every object in the universe emits thermal radiation. But objects that are very cold would emit a very small amounts of radiation in a very large wavelengths. This is known as thermal radiation. And when we construct a theoretical model that tries to predict this kind of behavior, we invent a hypothetical object known as the black body. So a black body is an ideal body that emits electromagnetic radiation due to the thermal agitation of the atoms and molecules inside. However, the only emission comes from thermal radiation. In other words, there is no reflection of light from an outside source. So there is no additional source of radiation from other sources. So for example, the moon shines white as a full moon, but this is not thermal radiation or blackbody radiation. This is reflection of sunlight. So we don't want this kind of radiation to interfere with our model. So we define a black body as an object that would appear black at room temperature because it would absorb all the incident radiation. Therefore, any radiation coming out of the black body would be caused by thermal radiation and nothing else. Ideal black bodies don't exist in real life, or at least not at 100%. However, most objects that are emitting red light and radiation due to their temperature can be approximated as black bodies to varying degrees of accuracy. Charcoal pieces, for example, look pretty black. Well, here I have white, but they look pretty black at room temperature. But when you heat pieces of charcoal in a barbecue, you see that they glow red, and that reddish glow is thermal radiation and obeys the laws of blackbody radiation. So that's a very good approximation. Stars like the sun also are very high temperature objects, and they emit a lot of light, and this is also a very good approximation of a black body. And we will see later that it is an approximation, but not exactly black body, because there are absorption lines present in a star. But this is another discussion for another video. Consider a black body that is at a certain temperature. It will emit a certain amount of electromagnetic radiation. Now, it is obvious that a larger body at the same temperature has a bigger surface area and will therefore emit more radiation. So we want to express the amount of radiation emitted as function of surface area, so per meter square, so that two black bodies having different size would have, and having the same temperature, would be compared in a more similar manner. In other words, we would compare a meter square in each body, and we should expect the amount of light emitted to be the same in that case, assuming they have the same temperature. Well then, if we define the intensity of light on the surface of the black body as the intensity I, then it turns out, this is a empirical result, that the intensity is proportional to the temperature to the 4. This is known as the Stefan-Boltzmann law, and sigma, Stefan-Boltzmann constant, is 5.67 times 10 to the negative 8 watts per meter square for intensity, and then over Kelvin to the 4 to balance the temperature. This intensity includes all of the electromagnetic waves emitted by the object. Not only visible light, but all the infrared and the ultraviolet and everything else. And the higher the temperature, the brighter is the object. So this is all of the electromagnetic spectrum. The distribution of emission as function of wavelength is in a form that you are familiar with if you remember your physics NYC. This is called the Blackbody diagram or the Blackbody curve. Here we represent the intensity of light on the surface. Always remember, we are comparing objects by measuring how bright is their surface, and we are considering 1 meter square area. So the intensity on the surface per meter square per unit wavelength, or per range, per small range of wavelengths. In other words, this graph tells me how bright is the object for a certain very small range of lambda. Let's call that d lambda. This is a very small range. And then we can measure the brightness. This box is a small rectangle here. If you multiply di over d lambda, so the intensity per unit wavelength, multiplied by d lambda, the range of wavelength, what you obtain is the intensity of light for the range expressed here. For example, between 500 and 501 nanometer, I would have this much intensity. And then between 501 and 502 nanometer, I have another d lambda here, centered at a slightly larger lambda, and I will have a different area under this curve, a different rectangle here. So when I multiply this function of intensity per unit wavelength, multiply by a small range of the wavelength, I obtain a small increment of intensity. And when I add up all of these boxes together, what I am doing essentially is solving an integral. I am saying that the intensity, which is the area under the curve, is the sum of all of these little rectangles. And each rectangle is equal to the value of this function, which I call di over d lambda, the emission rate for each wavelength, multiplied by the range of wavelength involved in here, which is an infinitesimal, very, very small range. These bars gets very skinny. And what is the range of wavelength that we count? All of them from 0 nanometer, so this could be nanometer, up to infinity. So all the wavelengths from 0 to infinity. When you include all of the wavelengths and you add all of these boxes, what is the result? Yeah, the result is sigma T4. So this is the area under the curve. Okay. So this is called the emission rate per unit wavelength. What are the units here? Well, intensity is watts per meter square. And then we are dividing by wavelength, so per meter, for example. And then when we multiply by d lambda, we multiply by meters again. This cancels, and we end up with watts per meter square. So this graph represents the brightness on the surface of a black body for each wavelength. And the area under the curve will tell me what is the brightness that includes all of the wavelengths of the electromagnetic spectrum from gamma rays all the way to radio waves on the surface per meter square of a body. By the look of the graph, you can see that an ideal black body would emit a little bit of everything. So all of the electromagnetic spectrum is emitted, to various degrees. So there is a preferred region of the spectrum emitted with more intensity or more brightness. And the peak corresponds to a wavelength known as lambda max, the peak wavelength. And the peak wavelength for a given black body is inversely proportional to the temperature. And in fact, here there should be a constant of proportionality, which is 2.898 times 10 to the negative 3 meter Kelvin or something like that. We can double check this. I think this is correct. And so when you increase the temperature of the black body, when you increase the temperature, lambda max will decrease. In other words, wavelengths of smaller wavelengths will have a tendency to be emitted with more intensity, because as we increase the temperature of a black body, we increase the frequencies of vibration of the molecules. Remember, we increase the kinetic energy of the molecules, and therefore the frequency of vibration will stimulate the emission of higher frequency light, therefore smaller wavelength. So if I want to graph a second black body on the same figure, I draw a second black body with a smaller temperature. So let's say the temperature decreases by 50%, which means that the lambda max will increase by 50%. So instead of being at 6 division, it will be at 9 division. It also means that the intensity of light has decreased by a lot. And if I draw the graph of this second body, it will not overlap with the first body. Again, remember why. Because two bodies, we always compare a unit area. So it doesn't matter which body is bigger. We take a meter square of object A, and we take a meter square of object B, and we compare them. And for object B, which has a smaller temperature, sigma T4 will be much smaller. Therefore, the area under the curve will be much smaller. So object B would emit more of its light towards this wavelength here, but still emits less of anything when compared to object A. And now if I take an object which is 50% hotter than object A, so let's call it object C, then lambda max would be about here, and the intensity will be much greater. So object C, much hotter, will actually be probably off the screen here. Again, no overlap, because you change lambda max, you decrease lambda max when you increase the temperature, and you increase the emission for every single wavelength. All the molecules are vibrating with greater amplitude and greater frequency. Everything goes up.